Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Here is Maxim Sherlev. I would like to introduce him. He's earning his Bachelor of Sciences degree from Nizhny Novgorod State University. He's on the staff of the Laboratory of Physical Fundamentals and Technologies of Wireless Communication in the Radiophysical Department of NNSU. He has 10 published articles in Russian journals. His main research areas interests are in chip and programmable logic design, testing, wireless communications, and electrodynamics. And the talk today is on implementing a hardware CIL machine. So definitely a change of pace from some of our other talks. Thank you and welcome.
Let's get started. Our project hardware-based CIL-Machine, Nizhny Novgorod State University of Russia, Laboratory of Physical Fundamentals and Technologies of Wireless Communication. I'm a reporter Maxim Sherlev, and head of the project, Dr. Alexey Umnov. This is our team, hardware subgroup, software workloads and tools subgroup, and support and consultants, and head of the laboratory. And this is my agenda. I will tell about introduction, architecture of the CIL processor, description of the DSP core and CIL core, speed up features of the CIL core, and garbage collector implementation. And I will show example of DSP workloads for the processor, and development board for the processor implementation and hardware implementation results, software support and libraries, and conclusion and some comparison. The main idea of our project is to provide a mobile power efficient platform for executing CIL code. As the mobile devices market growth is very high and the digital home concept increases its popularity, the CIL hardware processor may be a key component for future digital home control entertainment systems. And the utilization of the stack-based hardware microprocessor, which represents stack-based programming model like Java virtual machine or CIL virtual machine, has many advantages and disadvantages. The stack is a serial device, and their maximum execution speed of CIL instructions cannot be more than one instruction per clock. At the hardware point of view, the stack machine is the most simplest way to execute some machine code, as instruction decoding and processor structure is very simple. Such a structure has limited ability for parallel execution, but low power, low complexity, and low power consumption. And here we have an important question. What is the trade-off between simplicity of hardware implementation and execution efficiency? This question escalates other important question. What kinds of tasks must be executed efficiently on the target hardware processor? Just now, .NET technology has such direct competitor as Java technology, which mainly is used in mobile devices like smart cards and mobile phones. The target of PDAs, laptops, desktop computers requires processor with usually high computational power, despite of consumed electrical energy. Market of mobile devices distinguish from computers in requirements to computational units, high computational power with very low energy consumption. .NET software is intended for execution model once written, executed on any platform, for software transmission over internet and safe execution over different hardware platforms. .NET technology is intended for different-oriented web services, distributed business databases, online transactions, CRM systems, support, and so on. The hardware CIL processor allows us directly support of .NET software inside different mobile devices. CIL processor is not supposed to compete with desktop processors and PDAs by performance, but it's great for mobile market and digital home. The target is end-user specialized and oriented for mobile devices, web terminals, web browsers, interactive TV, and house control system. Where desktop computers and notebooks have too much computational power, but mobile phones aren't ready to handle quite a big application. And we have requirements for the CIL processor. Execute .NET CIL code directly. .NET is native code of the processor. Consume low power from power supply, mobile low power devices, and efficiently handle DSP tasks. New generation of interactive multimedia mobile devices. And let us discuss about the architecture of processor. This is a high-level structure of the CIL process implementation programmer's model. CIL instruction decoder intended for direct execution of downloaded from internet business application code. This is just a second. This is our application distributed from internet and CIL instruction decoder with standard CIL class libraries and so on. And meta-information is processed using DSP-optimized libraries, multimedia libraries. And the programmer has two sets in one processor, instruction sets, DSP and CIL. Depending on desired execution modes, the processor decoder can be switched between DSP and CIL, instruction set decoding. At the hardware point of view, there is a DSP processor which has all classical distributed attributes, like dual address and data buses, dual address generation unit, and high-performance macro unit. The processor has two instruction decoders. It allows decoding of the native DSP and native CIL code. Execution of the CIL code is supported by internal control buses for the access to meta-information and additional direct mapping caches intended for caching of mostly used object and class information. This is a high-level hardware structure of the CIL processor, hardware structure. The CIL processor has structure which is extended version of the classical DSP one. The processor has four external buses, main X and egg and secondary egg bus are used for arithmetical data transfers from to caches and external memory, and X and egg space address bus for used for addressing, forming, and for memory access. Main data information unit, like this, is used for general computations, and X and egg bus address generation unit from address for memory. This. And the native DSP set instruction decoder decodes native DSP. This. And CIL instruction decoder maps CIL instruction set into units control signal. The CIL decoder operates jointly with caches for meta-information, which are intended for speeding up common object model operations for CIL. And but there is a question: why DSP-based? Is it a waste of time during development or necessary thing for digital home? As a CIL processor is excellent solution for digital home, we have a pro. We have firmware layer for executing very complex CIL instruction, which cannot be implemented as hardware, as CIL projected as a virtual machine. and increased in 5-10 times performance in multimedia in applications. And we have a contra increased development time, of course, and we need to implement only standard CIL set, not DSP. As a hardware point of view, we have pro effective and low power consumption computational kernel, good mapping CIL instruction to DSP instruction, low power consumption in multimedia tasks, similar technologies to executing and efficient ARM Java GZL. And contra, only serial instruction execution, as we have CIL stack based instruction set and don't want to use SSCLI techniques. In conclusion, why DSP based? We have 2-in-1, 2 native instruction sets on board. Complex CIL instruction, for example, hierarchy checks and safety checks, are simply implemented in firmware as DSP instructions. In 5-10 times increased speed improvement for DSP workloads and low overhead in terms of extra transistor on chip. This is a description of DSP core units. Here they are low on the left hand. The first, the low is divided into 2 parts. The first upper part consists of 2 multipliers. Just a second. This and this. And this scheme allows to perform 2 multiplications simultaneously, shifting before and after multiplication, and results of multiplications are handed in temporary product register. And the second part, this, consists of several functional units and a register file. A quadruple adder is intended for complex number computations, and 3 output of the functional units are multiplexed to via ports of the first even registers and second part odd registers of the register file, which can be read and read independently of one another. And the address generation unit on the right hand must support most address generation units schemes, like is the register plus immediate offset, which with automatic programmable increment or decrement pre or post, and circular window for convolution and bit reversing addressing. And at the next slide, description of CIL core. Under the execution CIL mode, the programmer has the exact implementation of ECMA 335 standard CIL engine. In comparison to DSP processor, the CIL engine needs additional hardware to operate with 1, 2, and 8 byte register values, pointers, object references, metadata, tokens, and floating point values. It supports spacing arguments in stack frame for local variables, and automatic creation of the stack frame. The CIL engine must also check types in runtime, and all memory operation must be agreed with CIL type model. But it appears that only several CIL instruction may be directly processed as DSP instruction, and therefore CIL instruction differs from DSP instructions significantly. The CIL pipeline is at least 3 stages deep for the simplest instruction, and the CIL code is prefetched in usual way. But instead of DSP, CIL instruction has 1 byte in size, so 2 bytes for extended instructions, and may have 1 byte or 4 byte parameters. And DSP prefetched unit is extended with the CIL instruction buffer, and CIL processor has Harvard architecture with separated data memory and program code memory spaces. And about speed-up features of CIL core. Meta-information cache. And the meta-information cache is one of the most important concepts of the CIL processor. Several most often used meta-information tables are selected for further use as cached meta-information. Initial meta-information tables is processed to have smaller tables with information, which is very important for acceleration of CL object model instruction. For each meta-information table, a separate cache is implemented. The cache memory is organized of blocks of similar structure, shown at this slide. Such a structure is quite simple, allows fast and scalable implementation of multi-way cache memories, allows efficient utilization of on-chip memory in FPGA field programmable gate array devices where there are usually several dozens of small RAM blocks. The first 4 bytes of meta-information cache cells are reserved for index, which is key ELSA, and then requested index and stored index are compared. If they are equal, the information which is linked with index will be loaded on the bus back to the decoder. And time of cache access must not exceed 1 cycle. And hardware type stack. Arithmetical instructions exit over the type stacks, which is represented jointly by a register stack, cache stack entries, and a stack in on-chip memory. The register file of DSP core is extended with type registers. The extension is quite straightforward to data register in address jointly with type register. The type register is associated with several different processing units which form the unified type operation support engine. The type processing engine includes 2 units. The type compatibility engine or operating type checking unit and type setting engine. The sources of units may be a type tag from memory, from register file, from meta-information cache, or it can be immediate value for type comparison. And the garbage collector is one of the key points of DSP platform paradigm, of course, and for the hardware CL implementation, the generational garbage collection methods was selected for the modeling and further hardware software implementations. For the building hardware support for the garbage collector, a solution was developed. The garbage collection algorithms could be implemented as 2 ways. A distinct thread traditional software implementation, which sometimes interrupts the calculations and tries to free unused memory. And more interesting way, a distinct processor which runs the garbage collector simultaneously with computations on the main CIL processor. It could be special coprocessor based on reduced DSP kernel. And this I will try to show you an example of DSP workload. Our CL processor is an excellent target for multimedia applications, and the following figure shows the structure of the described software-based graphics pipeline, and the concept of homogeneous coordinates is used. Just a second. It looks like this, and this is this workload. Look at our processor. The same as desktop processor. And next, development board. The prototyping stage closed the CIL hardware processor project, and the stage results can be used for future CIL processor fabrication in silicon in industry. For example, using 0.13 micron technology. The hardware CIL processor is implemented with the help of development board, which has FPGA field programmable gate array, a chip and input-output devices on board. The implementation process is divided into two stages, the implementation and testing DSP and CIL core. As the processor design is developed in Verilog hardware description language, it can be simulated with common digital hardware modeling tools, but the simulation tools allows to simulate processor, and the simulation process is formal. It doesn't provide a kind of real hardware where we can run an application. A real hardware implementation assumes the use of hardware device which behaves exactly like the projected processor core. The FPGA prototype is used for CIL process implementation. It was a family of Virtex-4s with 15,000 logical element and distributed RAM. We have chosen the development board ML4001 from Xilinx, which most remarkable features shown in this slide. And next slide shows us our testing process for processor cores. The purpose of the core testing and verification process is ensure that the core complies with its specifications and all functionality is implemented in proper way. This is a critical phase of any hardware and software development, and we use the following scheme of the verification and testing, which is based on off-the-shelf software. We implemented two models using Verilog HDL and in C++. It should be noted that the C++ model is a full-scale analog of the Verilog HDL model, and the C++ core model is evaluated via PLI programming language interface functionality. And in verification and testing process, two types of faults are considered. First, an error in Verilog model and C++ model. But as C++1 is a similar model, the error probability in this model is significantly smaller than in Verilog HDL model, and C++ model is considered as the reference model. And hardware implementation results is shown on this slide. This table shows the evaluation of DSP core design on Spartan third and Virtex-4 FPGAs without additional optimization for particular chips. And we see that ALU consumes most of the FPGA resources. And our investigation shows that the DSP core used only small of part Virtex-4 and CIL process implementation regardless of appointment to core CIL processor design. It takes only up to 5,500 cells. It's approximately 35% of Virtex-4 if implemented without optimization. And with optimization, it should be smaller. At the next slide, we see screenshots of DSP kernel, and part of this DSP is the main ALU unit structure, and bit manipulation unit part of the ALU. It maybe this. Yes, it's this, and the ALU is this. Next. And the implementation results moderate detail level structure of implemented CIL processor. We see this figure, we can see .NET instruction decoder, this, and .NET complex instruction pipeline for instruction which can be implemented as hardware, and type setting unit, type checking unit, metainformation. This is a speed up features. And about .NET instruction decoder consists of pipeline starter, stack control decoder, execution decoder, DSP, DAO, and AGU signal mapper, type operation decoder, prefetch operation decoder, type stack decoder, and all of these features of processor is implemented on hardware. This is our software support, full software support, which is consists of exception microcode for complex CL instruction implementation in DSP core. Class library may be ported from PC, supporting system libraries, input-output, memory management, and so on. Multimedia libraries for DSP core, for DSP mode, and user applications, just-in-time compiler for CL code if it's necessary. Compiler, we are using retargeted GCC version, and we have assembler, disassembler, retargetable units used with compiler. They're especially turned for CL core, and linker, and hardware software code design suite. And this is comparison. This is comparison with some well-known implementation ARM-based software .NET engine for embedded system. It should be noted known as .NET CPU. This is a comparison of our hardware-based CIL-Machine and ARM-based .NET execution engine. We see that our frequency about 50 or 100 megahertz FPGA implementation with optimization, and instead 27 megahertz of DSP.NET CPU, ARM-based and silicon. And 1 CIL operation per cycle, it's about 50 millions of CIL operation per second instead of 450,000 CIL operation per second in .NET CPU. It's hardware-based CIL-Machine in 50 times faster than interpreted execution. And we have a hardware type control. Garbage collector may be implemented as hardware coprocessor or internal memory, intellectual memory, and the meta-information cache hardware. And DSP core with 2 memories instead of ARM core. And we have 2 multiply accumulate instructions and 2 ALU operations in cycle. Up to 4 instructions per cycle instead of 1 ALU operation in cycle in .NET CPU. And DSP core power consumption in 3-4 times less than ARM core. And this is conclusion. CIL processor is not only a software concept. It can be successfully implemented in hardware. And our dual architecture, the CIL processor has based on DSP core, enables multimedia applications with low power consumption. So the CIL processor may be successfully used for digital home and digital entertainment. CIL type engines are implemented in hardware. And hardware CIL implementation greatly outperforms non-optimized software implementation by performance and power consumption. This is a photo of our project participants. And gratitude for Microsoft Corporation, and which allows us to join people for different faculties of Nizhny Novgorod State University in one team, and Laboratory of Physical Fundamentals and Technologies of Wireless Communications, Nizhny Novgorod State University, which is supported by Intel Corporation for help during our research activities, and special thanks for Alexey Chepuzhenko, Intel Corporation, for spending his time advising us in hardware architectures. This is a question time.
The comparison that you have made, will you please go to that slide? The ARM processor,
Yeah.
in this case you have DSP and a CIL processor.
We have one processor, and this is processor has two instruction set. It's one processor with two instruction set, DSP1 and CIL.
Right. In the other case,
Yeah.
ARM-based execution engine, net engine, is it single processor performing the functions of the DSP as well as the CIL, or there also you have separately DSP?
And in .NET CPU, they have an ARM processor with software implemented CIL. As this is a open used way for CIL. We have some processor, and we can software support. We can make software support for supporting CIL. But our processor has a hardware supporting. CIL is native code of this processor.
Another question. In the hardware block diagram for the CIL processor, you have shown instruction buffer, instruction pipeline, followed by instruction decode.
Yeah.
It's not clear to me how you have instruction pipeline followed by instruction decode. Once you say instruction pipeline, general understanding is that you have the instruction decode, fetch, decode, execute, and then.
Okay. For simple instruction set, which can be implemented as hardware, we use pipeline. We don't use pipeline. It's as a native instruction. And if we have a complex instruction which cannot be implemented as hardware, we go to DSP mode. And in this mode, we can implement it in simple DSP instructions. This is a complex instruction with using pipeline. It is the best way for execution complex instructions. These instructions can be used doing faster in this mode. But the main way for executing CIL instructions is using CIL as native code. Yeah.
DSP code normally has fixed point arithmetic.
Yeah.
So what do you do?
We're using for 2-byte for floating point and for floating point operations DSP mode, and we chosen DSP mode, and we chosen pipeline, of course, and in this mode with a pipeline, we operate with floating point. Yeah.
FPGAs are very power inefficient devices.
Yeah.
So if you tell me that you implemented something like state machine of an FPGA, and you compare it against ARM, which is power very inefficient, and you get amazing results, I wonder exactly why that is. And maybe the only way I can understand that being so is that you have a benchmark that makes heavy use of the DSP part of your design, which is something that can be reasonably efficiently implemented on the system. So please tell us something about the benchmark you ran. Why did you get this result, which is the opposite of what my intuition would have been for?
A question about power consumption is based on DSP. We have a classical DSP unit. This is a classical DSP unit has approximately
I believe you've got good DSP, but is your benchmark something that makes it a benchmark in which almost all the work is really going to DSP and very little of it is going to the your .NET engine?
Yeah.
Okay.
If we have for power consumption, we use DSP only. This is not only DSP as a power consumption engine. This is a way for consumption. And ARM-based is a RISC processor. ARM is a RISC processor, and this processor has more power, using more power. Power consumption is less on RISC processor than it's on DSP.
A second question for you then.
Yeah.
If your objective is to try and reduce the power consumption of your applications, why not take the intermediate code and ahead of time translate it to the native code of some low power existing processor that's low power? Why not do that? Or why not have some kind of jitting which does that, so that you're generating code for a very efficiently existing low power processor rather than trying
Your question is that why we use DSP or not we use stack machine, yeah, for power consumption.
It's not about the DSP. Let's forget about that for the moment. You have explicitly implemented a circuit that interprets CIL.
Yeah.
Another thing you could have done was you could have translated the CIL code to the native code of a low power processor.
No, we have if we have a translation for native code of any processor, we have speed. We have low speed. It's represented in comparison. And now our processor, we have the the most fast execution mode. This is CIL is native code. This is most of the speed is large, high. So high, then it cannot be higher. And if we have a implementation of CIL into native code, our processor cannot have such high speed. Yeah.
Thank you.
Yeah.
So returning to the power consumption. This is normalized power consumption, meaning how much power you spend solving the same task on both platforms, or is just pure power consumption on processors?
This is a power consumption for often used DSP processors. We compare with in power consumption way. We compare ARM processor with a DSP. And of course, FPGA implementation is most is less. Power consumption is less, and FPGA only for testing and was used only for testing and verification.
So it's pure processor.
Yeah.
Okay. Because this gentleman here claimed that he knows for sure that DSP processors consume much more power than ARM, so it got me confused somehow.
DSP processor is not doesn't have such high power.
Okay. And after all, if it is not normalized power consumption, then we can just go to the spec pages, right, and compare.
Please repeat.
I say that we since we know the types of processors, we can go to the spec pages and compare the power consumption, right? Because it's okay. Yeah. That's what I tried to find out, if it's normalized power consumption or not.
Yeah.
Thanks. Do we have any other questions?
Thank you very much.